Hello and welcome. Today we are going to be solving problem 7-85. This is from chapter 7. It's an internal forces problem, and beyond that, it's a shear and bending moment diagram problem. And so we can see in the problem, that's what it's saying. Determine or draw the shear and moment diagrams for this beam. So if we look at this beam, the couple things that we can realize right away is we've got this distributed load that's being applied. This load ramps up on both ends of the beam, reaching its peak distributed load of 600 pounds per foot across this middle span of the beam. Maybe the first thing that we can notice about this, and we see this in most of our shear and bending moment diagrams, in this course at least, is that there are no external forces in the X direction. There are no normal loads on this. So the only thing on here that can support a normal load is this pin here at A. So this could have an X reaction force, but since we see no external X forces on this, we're just going to neglect that for this problem. So we're looking at this problem here. The first thing to do is to draw a free body diagram. So I'm going to switch over to my page. I've already gotten started here. I've got my free body diagram of my distributed load here, and I've only just drawn the hollow diagram because the first thing we're going to need to do is determine these two reaction forces. And to determine these reaction forces, we're going to represent our distributed loads as resultant forces. So when we look at this overall load, we can see that it's made up of three shapes that we can recognize. So I'm just going to make that a little bit more clear here. We've got a triangle on the left, a triangle on the right. And so in each three of these cases, the resultant force is going to act through the centroid, so through the center of the rectangle. It's going to be 600 pounds per feet times 6 feet. And then on this triangle out here, our resultant load is going to be 1/2, since it's a triangle. 600 is the height, 3 feet is the base. And so this is going to be in pounds. This is going to be in pounds. And the last one out here, try and make that arrow pretty close to the same length, since it's the same as the one on the left. We have 1/2 times 600 times 3, and that's going to be in pounds. So now it's also going to be really important to determine where these resultant forces are acting. So we know that our centroid is going to be 1/3 from the base. And so if we switch our triangle like this, what I'm talking about here is if this is our triangle, 1/3 of the way up the height is where that force is going to act there. I'll just put a little red dot here. So the red dot on each of these is just showing where that centroid location is. So in this case here, I'm going to plot all of these distances. So if this overall triangle is 3 feet, that means this is going to be 2 feet. This is going to be 1 foot. This will be 3 feet. This will be 3 feet. This in here will be 1 foot, and this will be 2 feet. So we can see each of these. So now we've got our free body diagram drawn out. And the first thing that we're going to do is we're going to find our reaction forces. This looks like my marker is starting to run out of ink. See if it lasts through this problem. So we're going to sum our moments about A equal to 0. So we're summing moments about A over here. We're going to have the first one here is going to be the weight of this load here of our rectangle times the distance 3 feet. So we have 600 pounds per feet times 6 feet, which is the length that that load is acting at, times 3 feet, which is the distance from A. Now we're going to do this triangle on the left side. We can see that's causing positive moment. So we're going to add 1/2, 600 pounds per feet times 3 feet. And then this is going to be from A, we've got 3 plus 1 is 7 feet. Now we're going to take away the moment from the triangle on the other side. So minus 1/2, 600 pounds per feet times 3 feet. And this is only 1 foot away. And then finally, our reaction force at By minus By times 6 feet equals 0. So this gives us By is 2,700 pounds. And so we can look at this beam right here and we can notice that this is symmetrical. So if it's symmetrical, if our loading is symmetrical, our dimensions are symmetrical, that means that through symmetry, or you could have just done the same thing, taking summing moments at B, we're going to get the same value for AY, 2,700 pounds. Okay, so we've got both of our loads. I just realized the first thing that I wanted to mention was that the sheet that I'm using, this is the template for drawing shear and bending moment diagrams. And just to really recommend that you're using something like this, we've got our beam drawn up here, and then we're just going to transfer everything down into these other graphs as we work our way down. Okay, sorry for that aside. Coming back to this, so we now have our free body diagram. We now know our loads. And so then the first thing that I always recommend is I like to use a pencil and just carry faint lines down across my graphs for any points of interest. So this is basically at this point, this is going to be our reactions. Carry one here down at B. Carry one here down at A. And I'll carry it down at the end of the beam as well. So these lines make their way all the way down. I ran out of space with my ruler, but we'll adjust those if we need to when we get down to our moment diagram. Okay. So the first portion of this beam, we're looking at from 0 to 3 feet. This is where the free body diagram that we can draw up here of this triangle, we can draw this in terms of our length x. For any time x is equal or greater, I seem to do this every single time. I draw my logic sign before my values. For x is equal to or greater than 0, but less than 3 feet. And so I'm just going to quickly draw my free body diagram here. So this is our variable length segment here, X. This is my triangular distributed load, where I've got the resultant force acting down. This resultant force here of our segment is also going to be dependent on X, such that it's just 1/3 of this length X. Now, the peak of this triangular distributed load, this peak up here, or in our problem, we can see at the very tip, when X is equal to 3 feet, the peak is going to be 600. So if X equals 3, this value has to be 600, which means that this value up here is going to be 200x, such that when X equals 3, this is going to equal 600. And then we're going to add our internal loads at the end here, shear V, moment M. Okay, so we've got our free body diagram set up for our first segment here. We can now solve for our equations of equilibrium. Sum of forces in the y equals 0. We have minus 1/2 200x times x minus our shear force V equals 0, such that this whole term here is our triangle, where this is our height and this is our base. Move this up a little bit. And so when we solve for this, we get shear V is equal to negative 100 x squared. Okay, so negative 100x squared, we can now plot that up here in our shear diagram. So if x equals 0, our shear is going to be 0. If we look at the shape of this, we see it's a negative exponential, which means as x increases, this is going to exponentially get larger as we go. Such like that. Now, at some point, I'm only drawing to this point of interest where there's going to be this point load at B. So I'm just going to leave it when we get there. And we can see ahead, if this is a point load, this is a discontinuity. So this is going to cause some kind of step in my shear force diagram. Okay, so I want to know what this value is here, right as we are right just to the left of that step. So I'm going to solve for my shear at 3 feet equals negative 100 times 3 squared is equal to negative 900 pounds. So this value here, negative 900. So this is my shear diagram here. The next stage I can look at is my moment. Maybe we'll do our moment first, and then we'll come back up here. And this is where, when you're doing a problem, depending on what you're more comfortable with, if you want, you can draw the entire shear diagram and then translate it to your moment. In this case, for no particular reason, I'm going to do the moment one next and see what the moment diagram is shaping up to be, and then I'll move across the beam, doing both shear and moment in parallel. So for moment, we're going to sum our moments at point X, so right at the tip of this face. We have 1/2 200x times x times x over 3 plus m equals 0. So this is the same as last time where these first three values, this is our triangle. Our height is 200x. Our base is x, but this x over 3 is the distance to the centroid, this distance up here. So this gives us our moment is equal to negative 33.3 repeated x cubed. And so this is going to give us the exact same shape. We have a negative exponential. So as far as drawing the shapes here, even though these are different, they're going to be the same shape. And that's what we're looking for. So we can draw the shape and then we'll find what the value is at that point. So same kind of idea here. Some exponential downward. So we can solve our moment at 3 feet, negative 33.3 times 3 cubed equals negative 900. And this is going to be foot-pounds, which also reminds me I need to add in these values. Shear up here is in pounds. Moments are going to be foot-pounds. And so I just solved here. This is going to be negative 900 foot-pounds. Okay, so here we are. And now we may not be sure of what we do for our next step. We've just done all of this, but up here, now we're adding in this point load at B and then moving into this distributed load. And so for the next stage here, this is where how you organize your work becomes really important with these problems. Because I've got everything in here. Now I need to keep doing math and draw a new free body diagram for this section of the beam. That's going to include the triangle and the rectangular distributed load. So I'm going to do that on a separate sheet of paper, and then I can come back to this sheet as needed. So I've already got this started. I've drawn my triangular distributed load. I've got my rectangular distributed load. This section is a function of x as well. And I'm going to add in a few extra details here. So I already know that this triangular load, I found this already. This is 900 pounds. And it's 900 pounds down, such that we know that this is the full area. And so that area is what we actually plotted on our shear graph. So this is 900 pounds. This is acting through the centroid. We'll call that C1. Where this distance here is 2 feet. And again, this whole distance here is 3 feet. And all of these dimensions are going to be important when we're drawing or when we're doing our equations of equilibrium. So now we have our rectangular distributed load that is a function of x. So as x moves forward, our rectangular distributed load is going to get larger. So at the halfway point currently, I know that the magnitude is going to be the area under this rectangle is going to be 600 pounds per feet. And we need to multiply by this distance under here. And this distance is going to be x, take away 3, because we're not including the length of that triangle. X minus 3. And so that's this distance here. X minus 3 is the distance of just our rectangular load. And then finally, when we're going to be calculating our moment, we're going to need to know how far away this resultant force is. And so that's this distance here. Just adding it up here to try and save space. So this distance here is going to be half of whatever x minus 3 is. So we can put this in brackets, x minus 3 over 2. It's going to be half of that distance. So we've got our new free body diagram for our second section here from 3 to 9 feet. And maybe I'm going to label 2 where this C2 point is. Okay, so now we can work through and solve using our equations of equilibrium. So sum of forces in the y equals 0. We have 2,700 pounds acting up at B minus 900 pounds from our triangular distributed load minus 600 times x minus 3 from our rectangular distributed load minus our shear equals 0. So now our shear is 1,800 minus 600 x minus 3 . And so this is going to be the equation of our line for our second segment. So the important part here is noting the slope of minus 600. So the slope of minus 600 and actually even before we do that, let me lay these out so we can see them both side by side. Yeah, like that. So the equation we just found is going to be the slope of this next section here. Now, what I've kind of overlooked and what we can't overlook when we're doing this is what happens directly at this load. And so this is where we can interpret what's going on in our graph and just plot it directly on here. So we have a point load, a concentrated load right at this reaction force. We know that's 2,700 pounds. So that's going to be a step in my diagram here. It's going to be a step of 2,700 pounds such that it goes up like this. Kind of drifted a little bit off that line, but that's okay. So this step is 2,700. And therefore, this value at the top here is going to be 1,800. And so now, this is this next section. This is where this line applies. And we can kind of see this if we work this out, 600 times minus 3. If we take that out, that's going to give us positive 3,600, I believe. So that means if this line were to be continuous, it would go, if it were on the other side, it's not. I want to make sure that I'm clarifying here. This is only starts at 3 feet, but we're basically going to get a straight line coming straight down. And so this line is going to come down at a slope of minus 600. It's going to drop straight down. Now I'm seeing here that this slope is going to drop straight down. You can probably tell I'm hesitating to draw this because I'm saying in my head, I'm thinking, oh, if this slope is going to come straight down, that means it's going to cross zero. And it's coming down pretty dramatically. So maybe I should figure out where it's going to cross zero before I plot it. And so let's do that. I can come back over here and find where shear equals zero. And so I'm just going to sub in zero to this equation. So I'm subbing in shear equals zero in order to solve for this. This is going to be at x equals 6. And so x equals 6, it's going to be right in the midpoint of this beam. We've got 3 on this side. We've got, this is at 9, so 6 is going to be right here. And so it's going to look like this. Now, anytime you're drawing your shear and bending moment diagrams, as soon as your shear crosses zero, and this will be the case over here, we've already got the line there, but anytime your shear crosses zero, if this isn't a point of interest already, then we now need to make it a point of interest. So this is crossing zero right at the midpoint. So I'm going to carry this down to my moment diagram here. So the reason for this is our shear diagram, the magnitude at our shear diagram at any given spot is equal to the slope of our moment diagram. So if our shear diagram crosses zero, that means the slope is zero, which means it's going to be a maximum or a minimum. So in this case, we're going to want to know what exactly that value is in case that value is one of the more important values. So I'm going to continue like I was doing before and now solve for my moments for this same section between 3 and 9 feet. So we're going to sum moments about x equals 0. In this case, we've got 900 pounds. This is going to be equal to x minus 3 plus that one distance here. So it's going to be x minus 2. So we have 900 x minus 2. I just want to clarify what this is. This is the distance to the centroid 1 minus 2,700 pounds times the distance that's acting is x minus 3 plus our moment caused by our rectangular load here. This is going to be 600 times x minus 3. 600 times x minus 3. Now this is going to be the magnitude of our rectangular distributed load. We also have to multiply it by this distance that we found earlier. X minus 3 divided by 2 plus our moment at the end equals 0. We can solve all this out. This is going to give us our moment is equal to negative 300x squared plus 3600x minus 9,000. So this is going to be our equation for our moment at that section. So we said before that this value x equals 6 is important because that might be a max, or that will be a maximum or a minimum. So let's solve what that is such that we can plot it more easily. So we know that there's a max, moment max at v equals 0 at x equals 6. So our moment at x equals 6 is going to be minus 300x squared plus 3600 times 6 minus 9,000 is equal to 1,800 foot-pounds. So this is going to be our value at x equals 6. So now that we know that this is our value at x equals 6, we can plot that on here. What did I say it was? 1,800 pounds. So we can plot that right here. Call this 1,800. 1,800 pounds. So I know that this is going to be exponential as well. Oops, sorry, move that back on screen here. This is going to be exponential, where this is going to be the max. And it's going to come down like that. And then after this, so for the rest of this problem, maybe even I'll make a note on here. Just to speed things up. And once you kind of have a feeling for how the shapes are looking, it becomes a little bit easier to do this. So what we're going to do is we're going to use our relationships to interpret the last section of this beam. So we use these relationships. I'll come back to this such that we can see this. So we've got some of this already. And this is where I'm going to look at my fancy formula sheet for my shear and bending moment diagrams. So, and I was saying this before, so the slope of the shear at any given point is going to be the magnitude down here, or the magnitude of our distributed loading. So we knew that. This is minus 600. Therefore, this slope is minus 600. The change in the shear here is going to be the area under the loading curve. So we've got that already. And so we want to continue on this moment. So the slope of the moment is equal to the magnitude of our shear. So that's why right here at 0, the slope is 0. After this, we're going to get more and more negative. The slope here is going to get more and more negative. And we should be recognizing there's some symmetry here already. So if this is going to get more and more negative, that means it's going to, starting at a slope of 0, it's going to drop down all the way down here. And so this is going to mirror what's on the other side here as this gets more and more negative, like so. So this is going to drop down here. Okay, so now we're going to interpret the rest of what's going on here such that we can draw the rest of this graph. So the last part here in our shear diagram, we see at AY, we've got another 2,700 pound load. So that means this one is going to jump up 2,700 pounds again. Jump up by 2,700 pounds. And if we're down here, this was minus 1,800. This is going to be 900. So it's going to jump up 2,700 pounds with this discontinuity. We're crossing zero again, which means that we're going to have another maximum or minimum down here. We'll get down to that moment in a second. And so now we're up here where we're up at 900, and now we're encountering this triangular distributed load. And so the magnitude of this distributed load is going to be the slope of our shear diagram here. Now, a couple other things we can notice. The ends, because the ends are free ends in our problem, both of these ends are free ends. If we were to just take a sliver, an internal cut right at the tip, nothing is happening there, which means our shear is going to be zero. Probably should have pointed that out at the beginning when we started this. So our shear is going to be zero right out here. And so that means we got to get from 900 down to zero. The slope at 900 is going to be right here at this max. It's going to be minus 600. And then that slope is slowly going to turn into zero. So that means our slope is going to start out really negative, minus 600, and then ease off to become zero. Sometimes I like to just briefly shade these diagrams in, just so they're a little bit easier to tell. Like that. And now we can finish off our moment, where if this is our slope, that means right here, after we drop down here, our slope is going to be really positive. Similarly to our shear, we've got our free ends, which means our moment at the end is going to be zero. So we're starting here with a positive slope of 900, and then it's going to turn into zero. So slope here is going to be 900, really steep, and then it's going to turn into zero, just like that. And this is, we can kind of see now that this is symmetrical, so that's going to be minus 900. Similarly, markers don't work very well for shading in. I think you get the idea here. So this is our moment. And so there you have it. The really important part here is that we're identifying this 1,800 pounds. And this is why it's so important to identify where these locations are where shear crosses zero. It's going to be our maximum or our min. If we're designing this beam for some type of application, we want to know what this value is such that we can design it for this 1,800 pounds. And so this is 1,800 pounds at x equals 6 feet. And so there you have it. So the really important thing here is to show the shapes of these curves and then identify, especially on our moment diagram, any of these peaks or valleys in these main areas here. And so you saw that this one, maybe just kind of reflecting on this, you saw this one, we started off really systematically drawing our free body diagram, developing our equations such that we can start drawing our diagram. And then once we had some shapes, we kind of had an idea of what was going on. Then we went to our relationships between these different graphs. And as you practice, you can get better at that, such that you can go straight from your loading graph and immediately draw your shear graph, and then you can move on and draw your moment graph as well. I would just recommend that you don't do that until you've had quite a bit of practice, such that you can recognize those relationships really quickly. So thanks for watching.